Okay, now let's look at the details of this steps that I skipped over. Okay, the first step, you need to find the trapezoids intersected by the line segment SI. Here we're going to use the invariant. The invariant says that the structure that we have is a search structure for all the segments that we have seen so far. So in other words, this is a search structure for all the segments 1 to I minus 1. This means that I could find the region that contains, for example, the left end point of the segment SI. So for example, that. I could find that region following the search structure. Then I could simply check all the 4 edges of trapezoid. Well, technically it is not the top and bottom. I could search the vertical edges to find which one this line segment crosses. So that means I could figure out this line segment goes from this face to that face and finally to that face, and then inside that face I find the other endpoint of this line segment. So by simply walking through the old regions, or the regions inside the trapezoid made by segments 1 to I minus 1, I can find the trapezoids 1 to k intersected by SI. Okay, so that's quite easy. Then the next step is to replace them by the new segments. This step is also relatively easy because they take a look at this trapezoid. Inside this trapezoid, I have essentially a partial segment, a segment that goes like this, and then I kind of cut this into three trapezoids. Here I have a line that crosses the entire trapezoid. I can cut it into 2 trapezoids, and here I have the same situation as the other one. Okay, so this essentially is constant work per trapezoid. So it's not much more expensive than finding the trapezoid intersected by SI. And finally, the last step. This is the most complex, or the more complex part of this algorithm, and it involves removing these old leaves that represent these trapezoids in the old structure and replacing them by the new one. And the important thing here is that some of these trapezoids need to be merged. So for example, when I look at this trapezoid in the middle trapezoid and this right trapezoid, I have one region over here and I have another region over here. These 2 regions need to be merged to create this region K. And how do I find those things? Okay, so that's the more the important part of this this process. I'm going to leave that for the exercise classes, but basically let's assume that I know which ones to merge. The merging is done then by placing pointers to the same to the merged regions. So let me go back again to explain this part. So let's look at this trapezoid, this old trapezoid. This has been cut into 3 trapezoids, H, I, and then this part over here. So the H region is a valid region that survives the merging. The I region also survives the merging, right? But this region over here is going to be merged by this region over here. So in other words, the above of this segment SI, this segment S3, and the above of this other segment need to be merged into one region. And this is done by placing both of their pointers to the same leaf node. So the leaf node J is the result of the merging of 2 regions. So therefore there are 2 pointers pointing to it. Similarly, region K here is the result of the merging of 2 regions. Whoops. This region, this part of this region, and this part of this other region. And since it's the result of merging of 2, those 2 pointers point to it. So basically, you can think of this process as follows. After finding these regions, old regions intersected by the segment, you create essentially 4 leaves, up to 4 leaves for each one of these nodes that are going to be replaced by L plus 1, and then you merge some of the pointers. Okay, so for example, the above pointer from this one and this one needs to be merged. They point to the same leaf node. Okay, so that's basically how it works. So ultimately, we will get this new search structure, which is not a tree because of this phenomena, but it is clear that it is a search structure that includes the segment SI. So we have maintained the invariant, so therefore we have a valid search structure, and then we can continue doing this. So So what is the analysis here? The analysis is a little bit tricky. But we're going to express this in terms of k, which is this parameter here. It's the number of trapezoid intersected by SI. So this step number 4 is obviously O of k, because moving outside every trapezoid takes constant time. Replacing every trapezoid can be done in constant time, because every trapezoid is broken down into constant number of new trapezoids. And finally, again, in the exercise class, we're going to see that the step 6 also takes O of k time for merging and placing the pointers. So in overall, steps 4 to 6 and also step 7 all take O of k time. In the worst case, this is pretty bad. In the worst case, k could be n, so therefore we have n squared worst case running time, we have n squared space, and log n query time. And again, I'm going to leave this part for the exercise classes to build examples of an input that results in the following performances. But in the next videos, we're going to show that if we do this random step, random permutation, then all of these things essentially magically improve to optimal.